based on this pulse data, our objective is to optimize the performance criteria. Here, the performance criteria for some algorithm can be accuracy, or for some algorithm can be error rate. If it is accuracy, then the objective is to increase the accuracy. If it is an error rate, then the objective is to decrease the error rate. Now the question, how we can do those things? Those things can be done using some model parameters and hyperparameters tuning. The model parameters are optimized, and based on that, actually the performance is increased. Now here, to give a overview, this I have taken one example here. Say this is an example, and in this example we have a number of pattern here. One of the example is this, and here the number of input attributes 1 and 2. That's a BP and heartbeat, and here the class that's the output. So each of the pattern consists of 2 inputs and 1 output. So this kind of database we have now. Now, if we want to solve the problem, so first of all, we have to train a machine learning algorithm based on this historical data. So how we can train? After training, actually, we can find a linear discriminant function. Especially if we train this data set, then we can get this kind of linear discriminant function. That's called linear discriminant functions. And the first attribute is termed as x1, and that's what we have once a weight with that. And second attribute is termed as x2, and we have a weight with that. And class C is a bias here, if it is a neural network. So this is a discriminant function. Now, using this discriminant function, we can solve the problem. Now we're trying to visualize, so with a problem space. That's why if we consider this 2-dimensional database as a single-dimensional database, say we have only 1 input and 1 output, then the linear discriminant function should be like that. This would be the linear discriminant function. So this linear discriminant functions represents a line. Now say the 1-dimensional data is represented to the two-dimensional space. Say this data set. So X is the input data and Y is the output data. Now see, we're having a number of examples here. 2 classes are there because it's a classification problem. So one class represents a white dot and another class represents blue dots. So these are the pattern nature of the patterns in the space as a problem space, right? So what's our objective to solve this problem? And also we assume here that the problem is a linearly solvable problem, but most of the problem what we solve using say neural network, the problems are not linearly solvable problems, but here we have considered the problem as a linearly solvable problem. So what will be our objective here? So if you can make any boundary line here, right? If we can make a linear discriminant function which represents this line, then we can say the problem is solved. But the question comes, can we initially locate the linear discriminant functions here? The answer is no, it's not possible, right? So initially we can have a somewhere in the problem space. Say in this case, say initially the linear discriminant function is here. So when the linear discriminant function is here, now if you find the accuracy, because if you consider that one side of the linear discriminant functions represents one class, on another side of the linear discriminant functions represents another class, then if you find the accuracy here, then we can say how much is the accuracy? It's 10 by 16, 62%. Why? Because 3 dots classified properly and these blue dots classified properly, but these dots did not classify properly, right? That's why here the accuracy is 62.5%. Now again, we change the linear discriminant functions. How we can change the linear discriminant function here? You see that in this linear discriminant functions, we are having 2 constants. Which are the constant actually here? Y and X. We cannot change the values of the attributes. What we can do, with this attribute, we have a coefficient M, right? This coefficient can be changed. And also we are having another, this is called bias. We can change the bias. This coefficient we can change. Now we can change, if we change this one, then the locations of the line or the boundary, or you can say the linear discriminant functions will also change. Now by changing this one, say now it sits here. So when it comes here, then we can see that out of 16, 3 patterns can be classified properly, right? Therefore now the accuracy becomes 81%. So in the second iterations, we are looking at the accuracy increases from 62 to 81%. So in this way, actually, it optimizes the performance. And it does number of times the same thing, and finally when the line comes here, how the line comes here? Based on the values of these coefficients M and C, right? So once the line comes here, then all of the patterns could be classified properly. Then we can say 16 patterns are classified out of 16 properly, therefore the accuracy is 100%. Now the question is how we can change and how we can find the exact value of these coefficients, right? M and C. And see here, like if say it's a two-dimensional data set, say for an example, so one neural network can be like that. So each of the pattern can be applied here. So first pattern can be applied here. So here the first attribute, here the second attribute, right? And then we can have corresponding weights. Initially we can have say random weights here, or we can put here 0 0. Then we can produce an output, right? So then we match this output with the exact desired output. If there is match, then there is no learning. If there is a mismatch, then there would be a kind of learning. And based on that, actually, these weights would be updated. In that way, actually, the weights will be updated. And these weights are nothing. These weights are the coefficients of the input parameters. In that way, actually, the weights are updated. Once weights are updated in such a way so that this classifier or this linear discriminant functions separates the data or solves the problem, then it stops, right? So this is an example of the machine learning classifier here, and already we have seen here the definition of the machine learning. Then we're coming here, if you see the machine learning algorithms, now based on the learning paradigms, the algorithms can be categorized into three categories, and these are supervised, unsupervised, and reinforcement learned. In supervised, generally we do this kind of tasks, classification and regressions. Now to do these tasks, we're having number of machine learning algorithms right here: artificial neural networks, Bayes, decision tree. These are the conventional. There are a number of other machine learning algorithms, but these are the very popular and the conventional machine learning algorithm. That's why I have taken in a slide these things: neural network, Bayes, decision tree, support vector machine, in k-nearest enable linear regressions, and number of regressions methods can be here. If it is an unsupervised, then the tasks which are related to unsupervised learning, these are clustering and association rule mining. Those tasks again can be done using the neural network, k-means, k-meroid clustering algorithm, a priori algorithms, predictive a priori algorithm, and different machine learning algorithms are there. But one thing can be noticed here is still this clustering can be done using say artificial neural network. Then we have a reinforcement learning here. So we are having a number of say algorithms to solve the reinforcement learning problems, and here we have some of the algorithms we have shown here. This artificial neural network, deep neural network, deep neural network, and many neural networks are there. And apart from neural networks, many other algorithms are also there. So one thing can be noticed here: if you see all kind of learning paradigm, or all kind of learning paradigm can be done using artificial neural networks. Perhaps due to this reason, artificial neural network is considered as one of the most powerful machine learning algorithm to use in any kind of problem. All right. So in line of that, we have come here to what is actually an artificial neural network. So if you see the definition, there can be a number of definitions, but here one of the definitions which can be given for the artificial neural network is like that: artificial neural network is a data processing system, and it consists of large amount of or large number of interconnected processing elements in an architecture inspired by the structure of neuron cortex of the brain. So here we are going to deal with large number of processing elements. So you can see here one of the example here. So this is an architecture here. We can have a number of, these are the neurons, these are the neurons. Just it's a very small neural network. Just I have shown you for citation purpose. But we can have, when we think about a practical neural network, it can have a number of hidden layers, and within a hidden layers can have a number of neurons. So if you see here, it consists of number of processing elements, and all the processing elements are connected with each other. That's why it is said that they are the interconnected, and we are having large amount of processing elements here. So this is the structure. In one word, we can say it's a data processing system with number of processing elements. Now, this neural network resembles our brains in some ways, and these ways are how these ways are this. And by this neural network, we can acquire knowledge by learning, right? And this acquired knowledge is also stored for future use, like our human being. And also, how this knowledge is stored? This knowledge are stored in interconnection connections, right? Interneuron connections. So these are called the interneuron connections. You see that this is one neuron, this is another neuron, this is one neuron, these are the another neurons. So there are number of interconnections, and these interconnections are used to store the knowledge, right? These are called synaptic weights. Using these synaptic weights, we can store the knowledge which is say earned or which is acquired during the learning process, and this knowledge can be used for future use. So in future, if you want to solve some new problem, then those problems can be solved using these weights. And I try to understand, in every machine learning algorithm, the main objective is to extract the knowledge, and using that knowledge the problem will be solved, the next problem will be solved. In case of neural networks, if we talk about the knowledge means the weights. In case of conventional neural networks, knowledge means the weights. So the knowledge is stored in some of weights. Using these weights, actually in future the next new problems can be solved. Now we're coming here. Now we should see the characteristics of neural network. What are the characteristics? The neural networks learns by example. Already we have talked about. We can have a number of examples. Based on these examples, actually, the algorithm can be trained, and one of the you can say the linear discriminant functions can be trained, and these linear discriminant functions can be used later to solve some new problems if we're having say examples. So from the examples it learns, right? And then another characteristics, neural networks possess the capacity to generalize. It has the capacity to generalize. What is the meaning of that actually? We can have a large database here, right? We can have 1,000 and 1,000 data. So during training, this data can be used, right? So during training, from this data we can find out some kind of generalization knowledge. These are the weights, right? For an example, here how many we have an input attribute, pp, heartbeat, weight, and age, and finally the output is the class label. Now for this BP, from this database we can find out a weight. This weight represents the impact of BP in classifications, right? So this weight is here, right? And then similarly, we can find the impact of heartbeat. So that is in terms of weight. So this weight is represented as 52. So therefore, we have a WP here and heartbeat. Similarly, we can have weight for the here weight. So W3 is say multiplied with the weight here. Similarly, age can have. So for the age again, we're having some weight. These all weights are extracted or say found from the big database, right? Once the neural network is trained, then the neural network is not thinking about the database. It doesn't need the database to classify the new pattern. Rather, it needs the generalized weights, because during training, it finds the different weights for the different input parameters. Now onwards, these weights for the different parameters, these weights are required. So W1, W2, W3, and W4, these would be used for the further classifications of the patterns, right? So during classifications or during test, now the whole database, the database which was used for the training, is not used. So why? Because it generalizes from there. What kind of impact can have BP? What kind of impact can have say heartbeat? What kind of impact can have weight and say ages? So these only after training, these weights are going to be used for the classification. Therefore, we can say neural network possesses the capability to generalize, right? Thereafter, we have here neural network exhibit mapping capability. But once these weights are extracted, right? So even whenever some new patterns will come, the corresponding input attributes will be multiplied with the corresponding weights, and then automatically it can classify whether the new patterns belonging to positive or negative class. It can be multiple class. Just I have shown here one binary classification problem, right? Therefore, it can map. So whenever some input will come, then automatically neural network from the generalization capability, from the generalized weight, it can determine whether the new pattern should be mapped to yes or should be mapped to no. Means whether it would be positive or it would be negative. That's why we say neural networks exhibit mapping capabilities. After that, we are having here a neural network is nonlinear in nature actually. So in most of the cases, we don't see whether the problem is linear or non-linear. If our objective is to solve the problem with a neural network, blindly we use neural network. But generally it is assumed that if the problem is not non-linear, if the problem is linear, So to solve the linear problem, we should not use neural network. When the problem is nonlinear, only then we should use neural network, because a neural network is nonlinear in nature. Now the questions, what is linear and what is nonlinear actually? Now if we have this kind of data patterns, so this is one class blue, this samples represents one class, and orange this samples this one represents another class, right? So if we see these samples and if the samples are mapped in the problem space like that, then we can observe that this problem can be solved very easily by a single straight line. So when the problem can be solved by a single straight line, then we can say that problem is a linear problem. So if the problem is like that, then we should not use neural network. Rather, when the nature of the problem is like that here. So see here, blue dots, they represent one class, and orange dot, they represent another class, right? Now, if we want to solve this problem using a single line, then we cannot solve, right? One line cannot solve this problem. Now to solve this problem, at least we need to have two lines. So this kind of problem is called nonlinear problem. So it is generally assumed that when we have nonlinear problem, only then we use neural network to solve the problem, right? Now we're coming here. This is another characteristic. Neural networks are adaptive in nature because they adapt in changing environment by changing the scientific weights. So it's adaptive. So we can have this kind of database. Whenever we have this kind of database, then it generalizes, it learns the weights, and finally the linear discriminant function is represented like that. So we can have a weight, and a bias here, right? Now say the data is change appears there. So if the data set is change, because the situation can be dynamic or continuously can change, so database can be changed. If the database is changed, now this changed database can be used to the earlier trained neural network. So if we use this database to the earlier trained neural network, then again it finds the different weights. These weights would be a bit different. It would be different. Now we can still solve this kind of problem. So even if in the dynamic situations, we can use neural network. This is one of the characteristics, and there are some other also characteristics. I did not mention all those things here. And then neural networks are inherent robust as the performance is degraded gracefully under the adverse operating environment, and still can work. So neural network is robust in nature. What is the meaning of that actually? Now say a neural network is trained in this database, right? And if you see the data, the pattern of the data is more or less similar, or the data may be scattered. So after training, the neural network will find some weights. Again, these are the weights, right? And the neural network is trained in this database. Now say, during training, when unseen data is come, and the data is looking like that. Here, all the values, if you see at the BP, all the values are greater than 100. And now, in the test pattern, we have the value that is less than 100, that's 80. Similarly, here, all the values are less than 100, but here we have 100. Less than 100, but here we have 100. Similarly, here we have 40. So if we see the characteristics of these three inputs, these are completely different than the inputs which were available in the training database. But still, if this input is given to the neural network, then still it can produce some output. Still, it can produce some output. It doesn't mean that it cannot produce the output. Therefore, we can say neural network is robust. When we talk about robust, whether the output will be exactly right or wrong, we cannot guarantee. But we can say there can be certain kind of output, even if in the adverse conditions, because these conditions are adverse. Here we have 80, here we have 100, here we have 100, right? Then it comes, neural networks are fault tolerant as they can recall full patterns from incomplete, partial, and noisy pattern. It still can produce correct output. Same thing, here we have this kind of database, and the neural network is trained. After training, we're having this kind of weights here, right? And during test, we have a different kind of output here. So say, for example, one of the input parameter is missing here, just to have 60, 70, 60. Now, if this pattern is given to the neural network, it still can produce the output, and perhaps the output will be, say, the correct output. When it is a correct output, then we can say that is fault tolerant, otherwise not. And now say, pattern is a bit different. Here we have 80, 100, 140, it can produce output, and again the output can be correct. Okay, so if the outputs are correct, even if in the adverse condition, then we can say the system is a fault tolerant. So neural network is fault tolerant. And now we can conclude one thing here. Fault tolerant is always robust. Robust may not be fault tolerant. These are the characteristics of neural network. And finally here, neural networks are massively parallel in nature, which makes them fast for computation of certain tasks. What is the meaning of the massively parallel here? See carefully that we can have this kind of architecture. These are the input neurons. These are the input neurons, right? And these are the one hidden neurons. See, one hidden layer is there and two hidden neurons are there. Now, if you see carefully here, this is the hidden neurons. So the connection comes here. Then we can compute some of the output, right? Even if the output is computed here, now the output cannot be given to the next layer until and unless the computation is done to all of the hidden neurons, because still the computations of this hidden neuron is left. So again, the computations of this hidden neuron will be completed once all the neurons of the same layer is completed. Only then the information is propagated to the next layer, right? It means what? They are working in parallel. Even if we are doing the computation one by one, but it's not sending. The informations are not being sent to the next layer until and unless all the neurons of the same layers are computed. And once information of the all layers completed here, then only we're sending all the informations here, then again we're calculating. So the neurons are working layer by layer. It's until and unless all the layers are computed, the information is not passed. In that sense, we can say neural network is working in parallel. So these are the characteristics of neural network. So there are hundreds of neural network proposed till that. Different kind of neural networks are there. If you see the literature of neural network, but if you talk about working principle, the paradigm, how it works, there are certain popular neural networks. Their working principle is one by one. Just I have incorporated only those neural networks here. But in the same kind, there can be of neural networks. I did not consider, but I want to show you how it comes based on the working principle, one after another, right? So initially, when the work started, so initially, the first neural network model was proposed. That's called McCulloch and Pitts model. McCulloch and Pitts model, which was proposed in 1943. This was a first model, but this model was suffering with a number of problems, and these are the problems. Right? It non-Boolean inputs, means real value it cannot take. It can take only 0 and 1. The threshold is defined manually, right? Importance of all inputs is equal, even if the importance of some inputs can be higher. But in this model, there was no paradigm. All the inputs are having the equal weights here in this case. And finally, it cannot solve the non-linearly separable problem. Say it's a problem, it was not possible to solve by the McCulloch and Pitts model. So after that, McCulloch and Pitts model, after that, the Rosenblatt's single layer perceptron was invented in 1958. So here, most of the problems are sorted out. Perhaps most of the cases generally when you start say learning or when you say teaching neural network, start with say which one perceptron learning, right? So in perceptron, because many things were sorted out, that's why we start with the perceptron. Perceptron solves most of the problems of the McCulloch and Pitts model, but still the perceptron or single layer perceptron is suffering with one problem, that is it cannot solve the non-linearly separable problems. The XOR problem cannot be solved using a single layer perceptron, right? After that, it comes a multi-layer, the concept of multi-layer perceptron comes, and thereafter, the backpropagation neural network comes in existence. So in backpropagation neural network, most of the problems were sorted out. But again, in the backpropagation neural network, there was a problem, right? So backpropagation neural network can solve non-linearly separable problem very easily. But here we have the problem is what output depends on present input only. No previous input or no previous output is considered. Hence, it cannot handle time series data or sequential data. That was a problem in the backpropagation neural network. Simple backpropagations. Then thereafter, there are a number of amendments in the backpropagation neural network to consider that issue, but we are not going to talk about that. But initially, when backpropagation came That was the problem in backpropagation neural network. And thereafter, another kind of neural network comes, that's called recurrent neural network, around in 1986 actually. So this neural network was especially proposed. Why? Because it can handle time series data or sequential data, where output does not depend on only present input, but also previous input and output. Therefore, recurrent neural network came in existence, right? And thereafter, if you see the neural network nowadays, everybody is working with the deep neural network. So starting, or initially, the concept of deep learning was started in 1994, but it becomes most popular, and some of the problems are solved in the 2012 when the AlexNet is came in existence actually. Initially, in the this LeNet came in 1994, right? So now the questions why we do using the deep learning. So why not using the simple neural networks? So these are the reasons for, these are the explanations for that. These are the crystal clear explanations for why we are looking for deep neural network. So just I'm reading out all those things one by one to increase the accuracy when trained with huge amount of data. So try to understand, if you don't have a huge amount of data, don't attempt with deep neural network. It can never, if the data set is very small, it can never outperform simple neural network and conventional machine learning algorithms. It can increase the accuracy even when we have a big database, right? And the second point, when there is lack of domain understanding for feature introspection, it means what? If the feature space is not clear for a certain problem, to solve this kind of problem, the deep neural network use, especially the image data. The feature space is not completely clear. We use certain conventional tool to extract the different kind of features. Still, that's not clear. So in that situations, actually, deep neural networks will be used. Then to deal with unstructured data, like the text, image, video, these are actually unstructured data. So to deal with unstructured data, because in the unstructured data, feature space is not clear. We take some of the features and try to solve the problem, right? And here finally, deep learning eliminates some of the data preprocessing that's typically involved with machine learning. So when we use a deep learning, we don't need to bother about data preprocessing, especially feature extraction, feature construction, feature generations. Those things are not done in the deep learning. So if we don't want to bother about these data preprocessing, say, steps, then we can look for the deep neural networks. These are the regions we use a deep neural network. So it doesn't mean that if you use a deep neural network, you will get always a higher accuracy. Your database size should be very high. Only then it produces. There is a discussion, there is a topic on that actually. So here we talked about the most popular neural networks. Now, whenever we talk about neural networks, so we talk about the learning, how the learning is done in the neural network. Learning is done based on the updation of the weights. Now the question, how we can update the weights? Now to update the weights, we're having different kind of learning algorithms based on the learning rules. Based on the learning rules, these weights are updated. It doesn't mean that weights are updated always in the same way. No, based on different learning rules, weights are updated in different ways, right? So these learning rules are categorized here. The neural network learning algorithms or learning rules can be categorized into three categories. These are supervised learning, unsupervised learning, reinforcement learning, right? In supervised learning, we're having these are the conventional. There can be many more, right? But generally, most of the cases we use this kind of learning rules: the perceptron learning rule, least mean square, delta learning rule, backpropagations, then correlation learning rule. And then unsupervised learning, we are having Hebbian and competitive, right? Reinforcement learning, I did not include here. Then we're coming. So out of all those things, out of all the neural networks, we are going to mathematically the working principle of perceptron neural network or perceptron learning. So we're coming here. What is initially the perceptron, right? So perceptron is a supervised neural network. A perceptron is a supervised learning model. And this is especially used for binary classifications, right? And if we talk about the structure of the perceptron, it consists of 4 components. And these components are input values, weight and bias, net sum, and activation functions. Using these components, a perceptron consists of, right? Now, if you see pictorially, a perceptron, the structure of the perceptron is just looking like that. So here we can have a summation unit, right? And here we have the activation functions, and here we have number of inputs. These inputs are associated with weights. For each of the input, we're having weights here: weight 1, weight 2, weight 3, like n number of weights, right? N number of weights means what? It is expected that each of the pattern will come with n number of dimensions. The number of input features will be n, right? So one pattern consists of n dimensions here. So when pattern is applied here, the pattern will have a x1, x2, x3 up to xn number of attributes. So whenever the nth attribute comes here, the attribute value say applied here, this attribute value is multiplied with a weight, one weight. Similarly, this attribute value is multiplied with this weight. So each of the attribute value is multiplied with some weights. Now, what is the function of these weights actually? Now, some of the attributes can have much more impact than others in producing the output. So, if some input is having higher impact, then the weight of that attribute will be higher. If some attribute is having less impact, then the weight of that attribute will be lower. In that way, actually, all the input values comes with the weights, and which makes the summation unit, means net input. In the net input, also one more element is added here. That's called the bias. So bias is added to overcome the overfitting problem. So bias is taken here. The input value of the bias is always 1, and the weight can be changed, right? Weight can be changed. So in that way, this net summation is consist of. Now this net input is given to the activation functions. Once it comes to the activation function, then activation function produce some outputs. We're looking on that how it is, right? Already talked about all the inputs will come, right? So here, this is the equation how we can calculate the summation of the inputs. How we can calculate, this is the equations by which we can calculate the summation of the inputs here. And one thing can be noted here: if some of the input value say inhibits, means it doesn't have a positive impact, means it inhibits the decision, it is against of the decision, in that case this input will have a negative weight. If some of the inputs say in favor of the output, then the weight will be say positive. So weights can be negative and also weights can be positive here. And already you have seen that if some is having some more impact, then the positive value will become higher. If some is having less, then the positive value becomes lower. And finally, the total input can be calculated like that. Here we have a summation that is 1 I equals to 1 to n, and then plus the bias here. This is the whole input. We can calculate like that, right? Once input is calculated, already we talked about, this input is given here, and we can have the activation function here. This activation function is called also transfer function or the squash function, and the responsibility of this activation function is to produce some output, right? And this activation function also normalizes the value, right? That the value can be normalized in between 0 or 1, or in between 1 and -1, based on the nature of the activation function. And also, the activation function makes the neural network efficient. Therefore, nowadays there is a trend and research topic of activation functions. People are doing research in activation function. Now the question is why? Because if you think about neural network consists of thousands and thousands neurons. And with each of the neuron, there is one activation function. So now if the activation function is a bit complex, then the whole neural network is going to be complex. So we cannot find the output in say practical time. So the problem is going to be intractable problem. So therefore, people are doing research, and when we take say activation function, we need to take a simple activation function so that the neural network can be faster. Perhaps due to that reason, if you see the deep neural network, right? In deep neural network, we're not going to use a sigmoidal activation function, because if you see the mathematical part of the sigmoidal activation function, then it's a bit complex. In place of sigmoidal activation function, most of the time we use a ReLU activation function. The mathematical part of the ReLU activation function is very simple. It's a very simple activation functions, because in deep neural network it is believed that there can be 1,000 and 1,000 neurons. So if we have a complex activation function here, then the neural network is going to be very complex. Due to that reason, we use there the simple activation function, but the characteristics of the activation function should be nonlinear there, because we're going to solve some complex problem using, say, a deep neural network or deep learning, right? So now we're coming here. In case of here perceptron learning, we generally use most of the cases simple activation functions. If we use the activation function, that's a heaviside activation function. That's called actually binary sigma. This is unipolar signum activation function. If we use that signum activation function, then the output can be either 0 or 1. How? Based on these values. Based on the values. This value is what value? This is the net value, net input. This net input is given to the activation function. Now, based on this net input value, we produce, the perceptron produces the output. If this value greater than or equals to 0, then it produces 1. If it is less than 0 or otherwise, the value is 0. If we use the activation function, that is heaviside activation function. In the same problem, we can use a different activation function. Say we are using bipolar signum activation function. If we use this activation function rather than say heaviside or heaviside 1 activation function, then the output becomes like that. Here we can have, this is the input. If this input is greater than equals to 0, then the output is 1. Otherwise, the output is -1 here. So you see, in this case, the activation function ranges in between 1 and -1. But in this case, it ranges in between 1 and 0. So again, you just try to remember one thing. In the same layer, we should use the same activation function. We should not use different activation functions. So in neural network, activation function is having huge impact in producing the outputs or making the neural network efficient and correct output also. And now, if we see the whole activation functions, based on the working, how they are working, how they are producing the output, based on that, the activation functions can be categorized into 3 categories. And these are binary step functions, linear activation function, nonlinear activation function. As a binary step functions, these are the activation functions, signum activation functions. There's a unipolar signum, which can produce 0 and 1, and a bipolar activation function, which can produce 1 and -1. And linear activation functions, we can have some continuous output, not a discrete 0 and 1 kind of thing. If we want to have a continuous, then we can use a linear activation function. So here, one of the activation function is pure linear activation function. And then the nonlinear activation functions, which are prominently used in different neural networks. And these are some of the examples of activation functions which are used as nonlinear activation functions: binary sigmoidal activation function, bipolar sigmoidal activation function, ReLU, that's called rectified linear unit, leaky ReLU, parameterized ReLU, softmax, Swiss, and different kind of nonlinear activation functions are there, right? So this is about the activation functions. Now, if you want to solve one problem using the perceptron, so what do we learn in the perceptron? We learn the weights. How we can learn the weights? Based on some learning rules. In perceptron, these weights are updated using perceptron learning rules. Using perceptron learning rules. Now we need to understand how this perceptron learning rule works. Only then we can understand the working principle of perceptron. So here, my endeavor is to give an example of perceptron learning rule. So in case of perceptron learning rule, the changes of the weight as defined by this one, alpha del xi. Here this del is called the learning error, or that's called learning signal. And this is the difference between in the design and actual neurons response, right? So changes of the weights depends on 3 parameters, and these are the parameters. The first one is alpha. Alpha is called learning rate, which can be in between 0 and 1, right? We can take any value, but this value is having huge impact. That's a different topic also. So we can choose here any one of them. In our example, we are going to take 1, but in practical, 1 is not taken. And here, this is D. D is the learning error, right? Or the learning signal. And already talked about this, the difference between design and actual neurons response. So D minus O, this is the actual desired output. and the output which is generated from the neural network. And then that is represented by del, and that's called actually learning signal or learning error. And finally, we have xi. Xi is the input for which learning is done. For example, if you want to change the weight W1, then the input is X1, because for X1 we're going to change the weight. So if we consider the changes of uh, weight or changes of W1, then here Xi will be represented by, or in place of Xi we have to give the value of X1. So that's why it is written here Xi equals to, or Xi is the input for which learning is being done, right? So now we have this example. So this is a two-dimensional prop that the each and every pattern is having two dimensions or two parameters. That's why we have two connections here, x1 and x2. With x1 we have a weight, with x2 we have another weight here, right? So you can see here the simple a pattern is given here, a pattern. So for this pattern, the value of x1 is 1.5 and the value of x2 is 0.5. Okay, and the desired output for this pattern, because perceptron comes under supervised learning rule, so label data, so labels must be there and the desired output must be there. So in this case the desired output is 1. Now say these inputs are given and the neural network produces the output 0. How 0 is produced, I'm not showing here. In the later slide we have. Now say the neural network produces 0. So here the desired output is 1 and the actual response from the neural network is 0. So there is a misclassification, right? So whenever there is a misclassification, learning is done only there. Otherwise, no learning is there. If there is no mistake, there is no learning. In all the machine learning algorithms, if there is a mistake, only then learning is there, right? So here, desired output is 1 and actual output is 0. And how we can do actually? See simply here how we can change the weight now. So we're changing the weights as a W1. So here we have a delta W1. This is a small change. By delta, we're going to represent very small change because we're changing the weights. We're changing very small weights. So that's why it is represented as delta W1. So delta W1, how we can change the weight? Already we know this is the equations for that. This is the expression. So now alpha del x1, the value of alpha we have taken here 1. This is learning rate we have taken for the simplicity, that is 1. So 1 is here into here the learning error. The learning error is what? This is the difference between the desired and the actual. So desired is how much? 1. So 1 is given here. Actual is how much? 0. 0 is given into. So for which input we are going to change this error now, weight now? For this input x1. The value of x1 is how much for this pattern? Because for each and every pattern, the values of that attribute will be different. So here, the value of this attribute for the first pattern is 1.5. Therefore, we have here 1.5. Now, if we simplify this expression, then we will get a value that's 1.5. So the changes of the weight will be 1.5 for W1. Similarly, we're finding here the changes of weight for W2, right? So here we have alpha del x2. The value of alpha is what? 1, this learning rate. And here what? This is the difference between desired and actual. So this is 1 minus 0 into the value of x2, because this is the input for which we're going to change the weight now. So value of x2 is which one? This is the value of x2 here, the 0.5. So here we have a 0.5. So if you simplify these expressions, finally get a value that is 0.5. So changes of the weights for W2 is how much? Let's say 0.5. So now if you find the actual weight, it's updated weight. How we can find the updated weight or the new weight equals to old weight plus changes of the weights. That's the equations, right? So here the actual weight is how much initial we have taken. These are the initial weights. Initial weights are the random weights. You can take any weights, right? So initially say we have taken 1 here. So old weight is 1. So we have a 1 here plus 1.5. So now the new weight becomes 2.5. Similarly for W2, the old weight, how much? That's we have taken earlier. That's 1. Therefore we have 1 here. And the changes of the weights, how much? That is 0.5. So we added here 0.5. So now the new weight of W2 becomes 1.5. Therefore we have changed here the weights. So new weights of W1 becomes 2.5 after applying the first pattern. Similarly, the new weight of W2 after applying the first pattern becomes 1.5. So these are the new weights. Okay, now we're applying the second pattern here. So 1 1 like that. Say 1 1 is there, and the desired output is how much? 1. Actual output is how much? 1. So there is no misclassification. There is no mistake, right? If there is no mistake, if you come here, the changes of the weight, you can see that the changes of the weights become 0. How? You see here, delta W1, alpha del X1, the value of alpha is how much? 1. And here, this is the difference between desired and actual. So how much? 1 minus 1, so it becomes 0. So whole term becomes 0 here. Similarly, in this case, whole term becomes 0. So if there is no mistake, there is no misclassification, then there is no error. So therefore, if you see here, the changes of W1 become 0 and changes of W2 become 0, right? Therefore, the new weight, there won't be any kind of changes. So in that way, actually, perceptron learning rule works. Now we're coming to solve one problem here, which is a single layer perceptron. Here we have a single layer perceptron to solve n problem. So initial try to understand the n problem. Already everybody knows that one. So just we have taken here 4 patterns, the 0 0, and the bias is there. Bias, already I've told you, this bias is incorporated to get it from say overfitting problem. So we have bias 1 and the target value 0. Similarly, 1 0 0, 0 1 0, 1 1 1. These are the outputs. These are the target output, also desired output. And the bias, the input of the bias is always 1. Already we talked about. And here we have taken 0 and 1 because we're going to use only hard limited activation functions to solve this problem. Therefore, we are restricted here in between 0 and 1. If we want to make it say 1 and minus 1, then we have to use bipolar signum activation function, right? So we're coming now here. So in this case, actually, so if we map the problem space, this n problem, if you consider this is x1 and this is x2, so these are the patterns. These are the patterns which represents 0 class, and this is the pattern which represents 1 class. You see here the A 0 0, so 0 0. Say this is the origin 0 0, so 0 0 is here. 1 0, so 1 0 is here, right? So C 0 1, so 0 1, this is here. Then 1 1, this is here, right? This is here. So if you see carefully, it's a linearly solvable problem. So what's our objective now? Our objective is to locate the boundary line here. Once we can locate the boundary line here, then the problem is solved. But unfortunately, initially we will not get here. We'll get somewhere else. Then we have to shift the boundary line from here to here, then here to here. And this is possible if you change the weights only, right? So coming now to the algorithm, how to solve this one. So in case of perceptron, single layer perceptron, now we're solving say n problem, and the algorithm is like that. First step of the algorithm says that initialize all weights and bias with 0 or random numbers. So we can keep 0 or the random number for all the weights. So how many inputs we have? 1, 2, and 1 bias. For bias also we must have weight. So initially this weight is 0, for this input weight is 0, for bias input is also 0. So all are initialized with 0. We can give here random values, there is no problem. But just I have given here 0 0 0 for all the input values and the bias. And thereafter and then keep learning rate in between 0 and 1. So to solve this problem, I have taken learning rate, that's a 1 only for the simplicity. And then second step says continue the loop until termination criteria is reached. So now the termination criteria can be 2 or 3. So here just most of the cases there are 2 termination criteria considered, and these are number of epoch or the error rate, right? So error rate means what? As we know, this is a linearly solvable problem, so we expect that the error rate would be 0. Or we can see that until and unless the number of epochs, until and unless the problem is solved, right? And then we come to step number 3. For each training patterns, do the following. So each training pattern means what? Here in this database, how many training patterns we have? In this database, we are having only the 4 patterns, and these are 1, 2, 3, and 4. So for all the patterns, what do we need to do? We need to execute step number 4 and step number 5. So step number 4, what it says? Calculate output responses of each J. In J means for each of the pattern. The patterns are represented by J now. We need to calculate the output response. So how we can calculate the output response? Initially, we have to calculate the net input, and this net input should be given to the activation function. Only then we can find the response. All right. So here by calculating the net input. So net input is represented by Yj. Okay. Now, so this is Ya because the name of the pattern is A. That's why I have written here Ya. And how we can calculate? By these equations. Already we know summation of I equals to 1 to n if we are having n number of dimensions, but in this problem we are having 2 dimensions only. So it will range I equals to 1 to 2, and then plus BW0. B means the bias, the weight of the bias. So here we're coming. So number, which are the input? Input is this one, right? This input is multiplied with this weight, right? Therefore 0 into 0 plus we have another input x2. This x2 is multiplied with this 0. There is 0 into 0 here plus which one? Bias into weight. So bias is only which one, right? And initially we have taken the weight of the bias is 0 here also. Therefore we have 1 into 0 here. Now we calculate the whole net input, it becomes 0. It becomes 0, right? It becomes 0. So the value of yj becomes 0, right? If it is 0, already here instead the activation function to produce the output response, because we have used here hard limited activation function. So here the value of y0 is 0. If it is 0 greater than 0, this condition is satisfied. Therefore, the output is 1. Okay. So you see here, this I have written. The target is how much? 0. Target is 0. Okay. And the output response which is generated from the neural network, how much? That is 1. So there is now error. How we can calculate the error? T minus y equals to 0 minus 1.
5 more minutes.
Okay, fine. So here the error is -1. We have here error. Okay. So now we're coming here. It's step number 5. It says that update weights and bias if t not equals to j. It means what? When the target and the target output, means the desired output and the output which is generated from the neural network is not same, only the learning would be there. See here. So this condition is satisfied. How? Because target is 0, means desired output is 0. But the actual output from the network is 1. So t not equals to O. That's true here. If this is true, then we have to update the weights in this way, right? This is the equations to update the weights. So new weight would be old weight plus changes of the weights. So we are coming here for the first pattern, for the first one, WA1 for the first weight. So what is the old weight? 0 is the old weight. Initial weight is 0. So the 0 is here plus learning rate is how much? Plus this one. So this is the learning rate. Learning rate is 1 into, and here del error signal is how much? -1. So here -1 into xi is how much? Xi is 0. 0 here. Now we simplify the whole expressions, then it produces 0, right? So changes of the weights for the first weight is 0 only. Similarly, for the second weight here, we have a 0. The old weight is 0 plus the value of this alpha, lem, del, and x2. Alpha is 1. Del is -1, and the value of x2 is how much? That's a 0. Therefore, again, the expression produces 0 here. Now we're coming for this one, which is B, is a bias. For bias is what? Equals to what? Old weight of the bias, that is how much? That is old weight is 0 plus alpha. Alpha is how much? This is 1. And this is how much? Del is how much? -1, right? And for the bias, we are not considering xi, because the value of xi is only 1. That's why it's not considering the bias. So now if we compute, then we'll get the value that's -1. So these are the updated weight. These are the updated weight, right? So this is the old weight, and now this is the new weight. 0, 0, -1. So if we do the next calculations for the next pattern here, we'll take the second pattern. But in this pattern, we have to take this weight. Now the weight will change. 0, 0, -1. Using these weights, we have to do the same procedure. Then we have to update the value. In that way, you have to do, and we have to stop for the iterations when all of the patterns classify properly, or there is no error. In that way, because to complete the computation of this problem, we need to have how many epochs? We need to have 6 epochs. So it takes long time. So it's not possible to complete here, but in that way, in the same way, how we change the weights, just we have seen here. Thank you everybody. You can have any questions. I'm ready to encounter the questions.
Thank you so much, sir. Yes, participants. So is there any question from your side? A few questions from your side. Participants, is there any question from your side? officers, students, anyone who have any question, you can use this. Would love to hear some questions. So otherwise, if you want to just share your experience of whatever you have learned from this, you can share it.
But Monali, if there is no questions, then thank you.
Thank you so much for your time, sir. I think everyone has really understood or like have really got the basics about the neural networks. It will be really helpful for all of them. And it was really our pleasure to have you with us. We thank you on behalf of the whole School of Computer Science and Engineering at the IGP University for joining us. It is really our pleasure to have you, sir. Thank you, sir.
Thank you, everybody.
Thank you so much. Thank you so much. With this, we conclude today's guest lecture session. Thank you, everyone. Thank you for your time, valuable time.